Hi, my name is Bhargavi Lenka.
My name is Brian Charan.
My name is Rohan Jinturkar.
My name is Daniel McKeon.
My name is Nivedita Sivakumar.
And we are here to discuss the development and implementation of a hygiene monitoring system. So before we begin, I'm just going to preview a little bit of what we'll be talking about in our presentation. We're going to start with the background, where we'll discuss key parts of what we're going to be talking about today. Then we'll transition into model development, where I'll give a general understanding of what our model looks like. Then we'll talk about system flow, which is essentially the implementation of our system. And then we'll move on to evaluating our system, basically talking about the implications and applications. And finally, we'll conclude with a brief question and answering session. The World Health Organization defines 6 motions as proper hand hygiene protocol. Please feel free to join us as we demonstrate these motions. So first we have the simple press. Then we have the roof, which gets the sides of the fingers. Next, we have the thumb motion. Then we have the webs motion, which gets the inner webbings of the fingers. Next, we have the mortar and pestle motion, which gets the palm of the hands and the fingernails. And finally, we have the link motion, which gets the knuckles.
The World Health Organization actually defines 5 specific moments when all healthcare professionals need to be abiding by in order to follow proper hand hygiene protocol. So those 5 moments are: first, before touching a patient; then before any aseptic or clean procedure, such as changing a patient's clothes; then after that, after body fluid exposure or risk, so for instance, a blood test; after touching a patient; and finally, after touching a patient's surroundings. Now, looking at number 5, that means that if a healthcare professional walked into a patient's room, touched the bed, did absolutely nothing else, and then walked out of the room, that person would still need to wash their hands in order to abide by the protocol set out by the World Health Organization.
Every year, thousands of people around the world die from healthcare-associated infections. In fact, 1 in 25 patients will contract a healthcare-associated infection while in the hospital on any given day. Hands are the main path of germ transmission, and so hand hygiene is an imperative measure. And in the state of New Jersey, a hospital must abide by the World Health Organization guidelines in order to properly operate. However, many hospitals lack a system to verify if healthcare professionals will abide by this protocol. And in one study conducted by the World Health Organization, it was found that only 22% of healthcare professionals adhere to protocol regularly. However, in that same study, it was also found that when monitored by external observers, these healthcare professionals' adherence to protocol increased to a staggering 52.2%. Thus, we observe a trend that monitoring healthcare hygiene, hand hygiene, and between monitoring hand hygiene and adherence to protocol.
As previously stated, when people knew that they were being washed while washing their hands, they were a lot more likely to actually follow hand hygiene protocols. That's why we wanted to emulate the same level of monitoring with the system so that we wouldn't need to have a physical human being stationed at every single sink in every single hospital. The purpose of our project was to develop a system that would recognize when proper hand hygiene is being followed in any healthcare environment. Now, in order to turn our idea into an actual solution, we used a variety of hardware and software components. Specifically, we worked with the NVIDIA Jetson TX2, which is a very small but very powerful embedded system, and it included many of the capabilities we were looking for. It also came with an embedded camera, which is what we use to record the vast majority of our data. Additionally, it comes pre-installed with Linux, which is a free open source operating system, and it allows for a lot more flexibility with coding compared to other options. Moreover, when we were deciding how best to create our solution, we settled on the programming language of C. And the reason for that was because, unlike other languages like Python, C actually compiles and runs very quickly. So if we wanted to find out whether someone was washing their hands in a short period of time, C would be able to best let us do that. Additionally, the main focus of our project was on machine learning. So that's the concept that one can provide tons and tons of images and tons of data to a computer in order to train specific models. We can take a look at that with an example with A, B's, and C's. If we wanted to train a computer with certain models for A, B, and C and help it recognize those letters, we would provide thousands of examples of each of those letters in the form of pictures. Then with all those pictures, the computer would form a model of what an A, B, and C would look like. Then, if we gave test data, the computer would actually be able to recognize those specific letters. Now, we use two specific machine learning techniques throughout our entire project. The first is k-means, which is what we will discuss later, and that's how we will separate the hands from the background. And the second is support vector machines, which is how we will classify each of the different hand motions.
Thank you. In order to fulfill the purpose of our project, we first have to develop a model for usage of machine learning. This process can be broken down into the 3 steps of data collection, image preparation, and model training. The first step of data collection simply involved the recording of a video where the 6 hand-washing motions were done properly. Then this video was sent into image preparation, where the video is split into individual images that can be processed with different algorithms and filters. This was done so that we could generate features from the data in a format readable by the support vector machine library of our choosing. Finally, in model training, we used this data to create a reference from the many examples we provided our machine with. This reference could be classified against new data that we collect in order to determine whether the new data has legitimate hand-washing motions. Now that we've developed a model, we need to create a system into which we can implement it. This system can be broken down, again, into 5 steps. First, we have recording, then image resizing, then image correction, data manipulation, and then at the end, where it's all sent through support vector machines. The first 3 steps of this process can be grouped together under the label of the image processing pipeline. The image processing pipeline begins with recording hand-washing data as images. These images are then resized and cropped so that they match the exact dimensions of the data we used in training the model. And then contrast with brightness is applied so that the hands can be more easily distinguished from their background. Finally, a Gaussian blur is applied. A Gaussian blur is a function that reduces noise in the images by blurring the colors of adjacent pixels. This facilitates segmentation in our next step.
After those initial modifications were made to the images, we had to make several more adjustments to make the images suitable for machine learning. First of all, in order to remove the bias that the backgrounds of the images would introduce into the machine learning training process, we used the k-means clustering algorithm to effectively remove those background pixels from the images. The k-means clustering algorithm segments an image into a given number of sections based on the differences in colors throughout the image. We use the algorithm, in our case, to segment the image into 2 sections, one group to contain the pixels of the background and one group to contain the pixels of the hands. Once we sent the images through this algorithm, we took all the pixels in the background group and we changed them into black pixels. This effectively made it so that those background pixels would not affect the models that were created during machine learning. Once we zeroed out those background pixels, we needed to format the image data so that it would be readable by the support vector machine library that we were using. To do so, we had to take each image and translate it into a series of features, where each feature is a single pixel, and each pixel is represented by a combination of its red, green, and blue components, according to that formula above. The red value times 100 plus the green value times 10 plus the blue value. And by that formula, a black pixel would be represented by a 0. Once we have that image data formatted correctly, we pass that data into the learn function of the support vector machine library that we were using, which was called SVM Lite. We trained one model for each of the hand-washing motions. To do this, we provided labeled correct positive and negative examples for each hand motion in order to train each model on how to differentiate between what is and what is not a match to that specific hand motion. In that image above, the lines in the center represent the model that the machine learning algorithm creates from those training images that we pass in. Once we have that model, we can classify new test image data through those models, through a given model, and we will receive a response of whether or not that image is a match to that particular motion. Based on this, we can take a set of images of a person washing their hands and pass those into each of the support vector machines. And based on the total number of frames that are determined to contain one of the hand motions, we can calculate the percentage compliance of that person to the complete and correct hand washing procedure. For example, if 8 out of 10 frames were determined to contain one of the hand motions, the system would return an 80% compliance. We generally don't expect a response in our system of 100%, Because in a normal example of someone washing their hands, not every frame is going to contain a hand motion. For example, during the transition from one hand motion to the other, as you can see, there would be a gap in that frame with no motion. So a percentage of 80 to 90% is generally acceptable and would represent someone washing their hands completely and correctly, whereas a significantly lower percentage, such as 10%, would clearly demonstrate that the person did not wash their hands according to the complete procedure. In order to test our system, we created a test data set containing images of all the proper hand washing motions, except for the link motion due to issues with data collection. We passed all these images through our image processing pipeline and then classified these images. Actually, we classified these images through each of the support vector machines, one for each motion. From that, we determined the percentage of test cases for each motion that were correctly recognized. So for example, take the simple press, as you can see in the chart above. We passed a certain number of images of the simple press into the support vector machine for the simple press. And we received a response from that all of those images we passed in were identified as the simple press. So basically, essentially, it correctly recognized those as that motion. We repeated this for each of the hand motions over two trials, and we observed an overall accuracy in the system of 75% in terms of its ability to correctly recognize the hand motions. You'll notice that the percentage for right over left web in terms of recognition is not 100%. We believe that this may be due to misclassification with the left over right web, which is visually similar, obviously because it's just the reverse motion. And as for the mortar and pestle motion, it also doesn't have 100%. It's significantly lower. Although support vector machines are known to be able to work well with small sets of data, we believe that we did not have enough training images to be able to, for the model to be able to accurately recognize that motion.
The fact that our system performed with the 75% accuracy shows that we have succeeded in developing a model that can correctly classify hand washing procedures. And our usage of the support vector machines shows that we also have succeeded in creating a system that can correctly classify hand configurations. Although at first glance hand washing does seem like a simple procedure to the average person, the statistics show that there are immense ramifications for a lack of regard to protocol and procedure. A successful implementation of the hygiene monitoring system has the potential to dramatically reduce the rates of infection and death around the world related to healthcare-associated infections. The system opens a path towards decreasing carelessness in healthcare environments where the decisions made are often matters of life and death. And also, the system could go a long way towards increasing the professional standards that are demanded for in these healthcare environments. In the future, the hygiene monitoring system could be implemented in hospitals around the world. Its unique ability to both monitor and identify correct hand washing procedure allows the system to give a more transparent perspective on the lives of healthcare professionals around the world. In addition, it could lead to a more quantitative viewpoint onto legal issues and liability matters that may arise as in medical lawsuits, offering a more objective viewpoint into the often subjective and complex world of medical lawsuits. The concept of the hygiene monitoring system also lends itself very easily to the food service industry, where obviously sanitation is a pressing issue with immediate consequences. By referring to the system's records, maintaining sanitation standards would be something that could be done with much more ease. And finally, on a broader level, the implementation of a hygiene monitoring system has proven the efficacy of classifying hand motions. And this could lend itself to applications such as identifying sign language using machine learning, which could increase opportunities for the hearing impaired. Looking ahead, we are looking to make a variety of improvements in the hygiene monitoring system. First, we'd like to get a larger data set so that the hygiene monitoring system can improve its accuracy when it finally encounters real-life hand washing. We would also like to run a wider variety of tests on the model. Right now, it is able to identify and classify hand rubbing with an alcohol-based solution, but we would also like to expand it to include hand washing underwater and the procedure that surgeons must do before operating, which includes washing the forearms. The removal of downsampling is a priority as well. Right now, we are analyzing every 5th pixel in every image instead of every pixel. This was done for time considerations and resource constraints, but obviously analyzing every pixel would also increase the accuracy of the model. We'd also like to increase the accuracy of the k-means algorithm, which is currently being used to separate the hands from the background in every image. Right now, it is operating under the assumption that the hands will always be in the center of the image, but this is clearly not always the case. And finally, we'd like to implement different kernel functions for the support vector machines. Right now, we are using a linear kernel, which classifies data around a line generated by the training data that we input to the model. But we'd also like to experiment with more complex kernels that could provide more accurate results. All in all, the implementation of a hygiene monitoring system could allow families to rest assured that their loved ones are in good and clean hands.
We had a lot of fun doing this entire project, and we could not have done it without the help of so many people. Just a few of them are listed here. So first, to our project mentor, Alex Wiener, he provided us invaluable support and hands-on support throughout the entire project. It wouldn't be possible without him. We also would like to thank Siddhi Shah, who unfortunately was not able to be here today, but she was able to coordinate all of our efforts. She was really keeping us going throughout the entire project, giving us the motivation to keep going. Additionally, the head RTA, Nicholas Ferraro, and also Brian Lai, who was our research coordinator, both of them worked with us on the paper and on creating this presentation. They gave us critiques throughout the entire process. Of course, this couldn't be possible without Dean Antoine and Dean Rosen, the directors of the Governor's School of Engineering and Technology, because they brought this entire program together and brought us all here today. Moreover, we'd like to thank Rutgers University, Rutgers School of Engineering, the State of New Jersey, Lockheed Martin, Silver Line, Rubix, all their corporate sponsors, and GSET alumni, because all of them were able to continue contributing to this program and make it possible for all of us. And so for that, we thank all of them, and we thank all of you for coming here today.
At this time, we open the floor to questions.
Yes.
My question is, how, you said that the motions were measured with alcohol rubbing. How do you think sudsing, washing hands with soap would interfere with your ability to detect the hand motions? And my second question would be, can your system account for not just the motion, but the length of time that, i.e. how long you're washing your hands for?
So I guess that's, to start, I'll start by answering your first question. That directly goes into our improvements. We need to test and make sure that we can do that. However, based on our k-means algorithm, which is supposed to block out anything that isn't the hands, at this time we're unsure to definitely give you an answer on that, but we're sure that it can be made possible.
The algorithms and method that we are using right now also depends on the color. So we're using, in order to separate the hands from the background or any image noise, we are using the pixel values and the colors, like as Brian mentioned, in order to do that. So perhaps if we had soap or water rather than alcohol-based solution, we might run into some interference with that, in that area, because if there was different colors, which is why we could look into implementing a stereographic camera, which depends on depth. So it would be searching the images for the actual hand placement itself, instead of relying on something as somewhat subjective as the colors of the pixels.
Additionally, if we wanted to maintain the primary features of our system in its current state, simply collecting more data, more image data of hand washing with that type of soap, suds, or alcohol-based solution, that would increase the accuracy in that area.
And for the second part of your question where you asked the duration, right now our model runs and captures video or images for 40 seconds, because on the World Health Organization, the average hand rubbing, like the recommended duration is 20 to 30, so we give them some leeway afterwards in case they take more time. However, we think 40 seconds will be enough time to perform every motion.
Our current system is working with just running for 40 seconds and taking pictures and then checking for all the hand motions within that period of time. But one of the improvements, of course, would be seeing how long is that person actually performing a motion, taking time to do the simple press, for instance, instead of just doing it for 2 seconds.
Yes.
I see that you use the Jetson TX2. Did you at all experiment with Cafe for your image processing? so that CAFE would have given you the leeway of exactly the same questions that they was asking about, like contrast versus pixel brightness.
Well, unfortunately, we received the Jetson TX2 a little bit late into the research process. So at that point, we had already used ImageMagick libraries on in the command line of Linux. So we didn't necessarily need to use the more advanced and efficient algorithms on the TX2. Thank you.
Was your system built like on a basis of taking the analysis, the pictures and all that, and then giving results later after running computations, or was it able to produce like instantaneous results? Like say, hey, okay, 40 seconds is done, you passed the test, you washed, or was it something that's like on a reporting function later?
The goal of that was really the second option, where after the person completes washing their hands, they would immediately know, or at least within a minute or so, if they had washed their hands correctly. One of the issues that we discussed that in improvements, was just time constraints, because running through the support vector machine especially took a lot of time to do. So one way to fix that would be to reduce the amount of time that it takes to run all those computations, so that way someone would get a result in a lot shorter period of time.
Although we should mention that training the support vector machines took significantly more time than testing it, so getting results was much easier than going through the initial processes of giving it data and training the model in the first place.
Yeah, I believe the classification process, which is when after the images are loaded into memory, only takes several milliseconds. However, the main time constraint is loading the images into memory, which we can hope to optimize by better filtering with our algorithms.
Increased processing power and stuff like that?
Yes, yeah. If there's larger memory and larger RAM, we could do it very, very quickly. However, on a Jetson TX2, the RAM was
So
not
you would
easy.
envision it being able to be like wash hands till the light goes on and then you're good?
Precisely.
Instantaneous.
Yeah.
Cool, thanks.
Yes, sir.
To monitor a healthcare worker every time they wash their hands, you need a lot of cameras. Did you give any thought to or discussion to the ethical questions about monitoring employees while they're at work?
So we had actually looked into the ethical considerations, and one of the reasons we focus on the healthcare environment is because in almost every single patient room, especially in major hospitals, there is a sink already there. So this would be specific to the sinks in those patients' rooms, not necessarily in bathrooms where there's different laws and different regulations. But within a patient's room, we would be able to have we'd be much more successful with also dealing with ethical considerations.
Not to mention, only the hands are captured and not any part of the face or any part of the body other than the hands themselves. Yes, sir?
You stated that your system looks for an 80 to 90% compliance rate with recognizing all the hand motions. Is there any penalties incurred for only doing, let's say, one of these hand motions as opposed to all 6 of them? And if not, how easy would that be to implement?
Well, essentially, that would be on the side of whoever uses the system. We will definitely provide the functionality to analyze the exact percentages, and like a hospital could do what they wish with it. However, we just are looking to show that it's completed or not. With the percentages, if they only do half the motions, the hospital could recognize that, put it into an employee database, and then maybe rate their employees on that. And however, we just want to show a pass or fail type thing with our system right now.
Yes, sir.
So the round of applause again for the school.